Okay, so here I have, it's a 5 Newton weight. Okay. So right now, what's the tension in this rubber band? Show me with your fingers how many newtons. Yeah, it's in equilibrium, more or less. I'm a little shaky today. Okay, gravity's pulling down with force of 5 newtons. It's actually 4.9 newtons, but I'm going to say 5. We got, brass is heavy today. Okay, and I've got to have an equal and opposite upward force. Otherwise, it would be accelerating in the vertical direction, right? Okay. Now, I spin this thing around. I think 1,001 is about 3/4 of a revolution. Okay. So I think it's probably about 1 1/3. I'm going to say 1.3 seconds to make a revolution. That's going to be important. Okay. And it's going around in, sort of a circle. My hand's wobbling a little bit, but you get the idea. Okay. Now, when it's out here, question is, what's its length? Well, we don't really know because we don't know the characteristics of this rubber band. So we're going to pretend the rubber band is nice and tight. Okay, it isn't. The further I swing it out here, the more the rubber band stretches. And why would that be? Well, you don't have, the recordings on, so you can't really answer me, but I'll probably let you tell me in a minute. Okay. Now, what we want to know is we estimate that when this thing is out here in its circle, that the angle with vertical is about 15 degrees. I'm going to just tell you the cosine of 15 degrees is around 1/4, because 15 degrees is about 1/4 of a radian. Is a small angle. You should understand that, but I'm not going to explain it. I'd be glad to, but time, So that's about 15 degrees. The sine is about 0.4, the cosine is about 0.9, and that's close enough just to make estimates. And you could refine that if you had specific numbers, as you will when you do the homework. Okay. Now, we want to figure out what the length of this thing is. Okay. And the length would be from here down to the center of mass. Okay, well, if we know that this is a 15-degree angle, and we estimated the radius of this circle to be about 10 centimeters, it's probably somewhat less than that, but 10 centimeters is convenient, then you should be able to tell me. Now, when I say the radius of the circle, I mean to the center of the mass, okay? 10 centimeters. So from here to here is 10 centimeters. Then how long is it from here to here? And I ask you to draw a triangle. Okay, well, it's pretty easy to draw that triangle, and everybody drew a pretty reasonable triangle, but not everybody had the length in the right place. So let's look at what that triangle actually looks like. Okay, so here's a good triangle. Okay, and this would be then the radius of the circle. I'll use a capital R for the radius. Okay, now where's the length of the pendulum? Some people had it here, but that's not the length of the pendulum, because the pendulum is out here. So this is the length. And here we have our angle. So what's the relationship? Well, I'm not going to drag it out of these. Should be second nature to you. That L sine theta equals R. It's however a sine of 15 degrees because we estimated 15 degrees. That was a convenient estimate. Because that sine is pretty close to 0.4 equals 2.5 times the radius. And if the radius is 10 centimeters, that's 25 centimeters. Okay. So it's pretty straightforward. And of course, that's not 25 centimeters, but the radius really isn't 10 centimeters. Okay. So we're just going to pretend it's 10 centimeters. We're not actually going to measure anything with this. I mean, that would be 20 centimeters right there. And that's all the way from the top to the almost bottom of the thing. Center of mass would probably only be about 16 centimeters, something like that. That means the angle is less than 15 degrees, maybe closer to 10 degrees. Wait a minute, is that right? It's 10 degrees, then the length would have been even greater. Now, well, radius is a little too big, but we're going to live with it. Okay, so does that make sense? Okay, so now if we do a free body diagram, we got the weight of the thing acting down. I'm going to use I and J because I find it very convenient. You can notate it any way you want, but this is a vector, so I want to write it as a vector. And then we have this, the tension. Okay. Now, what can you tell me about the tension? Well, the tension has an X and a Y component. So I just kind of ease out the tension, and now I've got T sub X and T sub Y. I could label T over here. All right. Yeah. That's nice. What can you tell me about the X component of the tension? Hint, this thing's moving in a circle. What do you know about a mass moving in a circle? Something reflexive that you should have learned back in the previous chapter that we haven't talked that much about. Okay, so what we got is, I gave you the hint. Things moving around a circle. Something you should learn from your Pearson materials. Okay. What do you know about a mass that moves in a circle? Well, if it's moving at a constant velocity, and somebody said it, you have centripetal force. So we know that I'll use capital R because I use capital R for the radius here. It's usually written with a lowercase r because big R is often saved for something else, especially when you talk about satellites and stuff. Right here, and it's what's the direction of the centripetal force? Well, centripetal means centra-oriented, okay, toward the center. So depending on where the mass is on that circle, the centripetal force is always toward the center. You just follow when it's here, centripetal force is in this direction. When it's here, centripetal force is in this direction. When it's here, centripetal force is in this direction, right? Always toward the center of the circle, which would be the equilibrium position of the hanging weight. Okay. Now, you see a centripetal force anywhere on this force diagram. Okay, now since I've specified a magnitude in a direction, I can put an arrow over this. And the center of the circle is in the same horizontal plane as the motion of this thing. It's in a horizontal plane so that the centripetal force has to be horizontal. There's only one place you can get a centripetal force here because the only forces acting on the mass are gravity and tension. Okay, now tension resolves into the x and y components. So you have T sub x. And I actually should say T sub x equals F cent because centripetal force is determined by things that we've estimated from the motion. Okay. So there's your centripetal force. From this, well, you can figure out velocity. I gave you the mass, 500 grams, implicit. Okay, well, I'm not going to write it out. And we estimated the radius of the circle. So we ought to be able to figure out the centripetal force from the radius of the circle and so forth, and see how close it is to 2.5 times the radius. All right, so you ought to do that. But right there is situation, and it is a situation for anything that moves in a circle is the centripetal force is mv squared over r. That's because the centripetal acceleration is v squared over r. That comes down to the analysis of an isosceles triangle. Okay. Again, you should understand that analysis. It's a chunk of knowledge that gives you a better perspective of things. Okay. Well, with that, you ought to be able to analyze. Now that's called a conical pendulum, and it's, I think, maybe the first problem in your assignment. And don't just use these as a bunch of formulas you blindly look at. Draw the picture, draw the free body diagram. That's how you get used to drawing free body diagrams and get an instinct for applying them, okay? Okay. Well, didn't plan to take that long on it, but what the heck. Okay. Now let's just say that this cylinder, let me get a little further from the cylinder is a hollow shell. Okay. Now, if it's a hollow shell, then if there's a mass inside it, the mass is going to feel what we call a centrifugal force. The mass is going to feel like it's being pushed to the outside. I thought it was pretty neat. I went to an amusement park in the DC area. It was about roughly the distance from here to DC from where I lived in Ohio at the time. Okay. I was 14 years old, seeing a girl I was madly in love with. She stayed with her aunt who lived next door. Okay. And she'd stopped coming at 11 because they were afraid what might happen. It might have. Although I think we both had no sense not. But, I was getting to the age where that could be dangerous. Okay. So anyhow, we went to an amusement park. And one of the rides in the amusement park was just a cylinder. Okay. They even had these, 100 years ago, whenever that was. Okay. They had a cylinder that went around in a circle, and it had this kind of fabric surface. Okay. And you'd get into it, and it'd start rotating, and you'd feel yourself pressed up against the edge of the cylinder, and then the floor would drop away, and you just stay there by friction. I thought that was really neat. Okay. And of course, when I took physics later, I understood more about it. I had a fairly good idea of what was going on. I mean, I knew it was friction. I knew it was being pushed that way, but I didn't have the tools to analyze it for a couple of years after that. Okay, so what if that cylinder that's moving around in a circle is moving around in a circle? And that's really a bad diagram. It should have been more elliptical. Should have been more elongated. You get the idea, moving around in a circle. Okay, so you have this centripetal force. mv squared over r. This is hollow. So inside, you've got this m1. Okay. Coefficient of friction is mu. Question is, will this block stay there? Okay. So question is, okay, here's the block. That is a horrible M. I don't know if you read. The block has a mass of M1. So what's a free body diagram look like? You're supposed to pause. Okay, well, we talked about this and we got some stuff figured out. Something I should have said back here, it's kind of implicit from the picture. Okay. The net force here is the centripetal force. Okay. And I didn't say that. It's drawn kind of like that's what it's going to be, but very sure that that tension is equal and opposite to this. Well, if the net force is the centripetal force, and the centripetal force is T sub x, then this component has to be equal and opposite to this one, right? Okay. In this case. Now the same idea is going to apply here. I think we're okay. Yeah. So this thing's moving around a circle here in a horizontal circle. So you know that the centripetal force is horizontal. Okay. So you know that the net force is horizontal. The centripetal force is not one of the forces acting on this thing. And the forces acting on this thing, and we kind of drew this out. You got gravity acting downward, obviously, right? And you got some friction that's preventing this thing from moving parallel to the surface, or hopefully is preventing it, okay? If the coefficient of friction is high enough. If not, it will slide, okay? And that gets a little bit complicated because in the radius of the circle this thing's on, gets bigger and bigger, so your centripetal force keeps changing, okay? So that's a little bit more complicated than what we want to deal with right now. So what we have right now is, okay, we're going to assume this thing's stationary and maybe figure out what this coefficient of friction is, or maybe we figure out what coefficient of friction is required to keep it stationary and see if it's high enough, okay? Okay, well, again, force is acting on this thing. Here's a dot representing this mass. You have the gravitational force. all right, is negative M1G times the J component. You don't have a centripetal force. I mean, yeah, you do, but the centripetal force is the net force. It's a sum of all the forces that are actually acting on this. The centripetal force is not something out there that exists independent of the other forces involved. Okay, so didn't say that very well. But anyhow, you have then what? You have the force exerted by the inside wall on the block. Now that's not the frictional force. That's a force between the surface of the block and the surface of the wall. Okay. You have the fact that in order to keep this thing moving on a circle, you have to have a centripetal force. Okay. Which means that intuitively, this is going to try to push out that wall. If it's a thin wall, maybe, and this is a very dense object, and this thing's moving fast enough, it might deform the wall. Okay. Well, what it does is it bends the wall a little bit, and the wall pushes back elastically, or by elastic compression. Okay. Force of compression. We talked about that weeks ago, so make sure you kind of understand that. Okay. Well, what you get is a normal force. That's what a normal force is. And the normal force has to be perpendicular if this angle is theta. This angle is theta, where implicitly this is the horizontal direction. Okay. And that's important. And then you have the frictional force, which is perpendicular to the surface, and the surface is that angle theta with respect to vertical. So you have a frictional force. There's your frictional force. These three forces have to add up to the net force, which is a centripetal force. Sum of these forces. What's the sum of these forces? The way I've done this, my J vector is vertically downward. Since these two forces are perpendicular, normal force is perpendicular to the surface and the frictional force is parallel to the surface, right? Always. It'd have been better to tilt my axis. Okay. So I'm going to actually, at this stage of the analysis, take that J off of there. I wanted to have it there to emphasize the fact that it's vertical. We're going to put the x-axis here, and the y-axis is going to go this way. Okay. Now, maybe that's a good idea, and maybe it isn't, because, of course, now the centripetal force isn't along the x or the y, so maybe we would have been better off with the x-axis here and the y-axis there. I'll let you figure that out. Okay. So I'm going to just put an arrow over this G, meaning that that's the gravitational acceleration vector relative to whatever coordinate system, rotation, whatever rotated coordinate system I might want to use. Okay, then it's plus the normal force plus the frictional force. And the centripetal force is m v squared over r. Implicitly the same r as we have here for here's using the capital R, probably bad form. So we use capital R down here. It's mv squared over r times a unit vector in the horizontal direction. Well, a unit vector in the horizontal direction, the way I've got it drawn right now, would be cosine theta I plus sine theta j. Your normal force would just be F norm times I. Frictional force would be F norm or F frictional times J, right? So we could ultimately write out the equations. M1G times cosine theta I minus sine theta j. This is M1G times a unit vector in the vertical direction with the rotated coordinate system. Okay, well, that's a little ugly and complicated. And then we have F norm times I plus the frictional force times J equals mv squared over r times cosine theta I plus sine theta J. We can set the I components equal and the J components equal. There's one more thing we do. One of these forces, magnitude of one of these forces can be written in terms of the magnitude of one of the others, and that eliminates a variable. So what can we do about that? Okay, looks like I don't have as much board visible. I thought we can fix that. There we go. Okay. Now I've kind of lost a little bit of this, but I've written it out here. So there's our equation, except now if we're in equilibrium, frictional force is mu times normal force. Now these aren't vector forces. The vector forces have I's and J's on them, the way I've written this out. Okay. So we end up with hope we understand that that's a little blurry. there's our equation. And what it then comes down to is the I component has to equal mv squared over r cosine theta. And the j component of all this has to equal mv squared over r times the sine of theta. Okay. So our final equations, write them out. What equation do you get by setting the I components equal? And what equation do you get when you set the j components equal? Okay, it's just very simple algebra. Got an I component, m1g cosine theta, f norm, and let's see this. And that's it on the left-hand side. And the right-hand side is mv squared over r cosine theta. Those are your only I components, and your j components are mg1 sine, m1g sine theta from here. Of course, a friction here, but that's u normal force. Okay, and then mv squared over r sine theta. Okay, I components, j components. Or if you want x components and y components. I like the I and j notation because it's simple to write. And you don't have to do a lot of bookkeeping. You just write out the equation and then identify the multiples of I and the multiples of j. They give you two equations. Okay, so let's just say we know the mass of this little block. It's, of course, a mass. And actually, let's see, you know, I was a little bit careless when I wrote this down. Nothing unusual. I just did that to illustrate another thing you want to watch out for. Okay, you got m1 a squared over r because it's this thing, okay? And of course, r is not the same r we had over there. You got to add the distance from here to here times the cosine of theta. And you can figure that out. If it was on a test and you neglected that part, a 10-point problem costs you 2 or 3 points, okay? So I penalized myself 2 or 3 points for not writing that down. So anyhow, these m's have to be m1. That's just bookkeeping. Okay, well, we estimated theta. So we know what the cosine and sine are, approximately 0.4, approximately 0.9. Just numbers. We can figure out what v was because we know the radius, at least if we believe our estimates, we know the radius. Okay. And just multiply by 2 pi, we got the circumference and we got the time it took. I'd say 1.3 seconds. I originally estimated 1.5. You might estimate it half a second. That's okay. Whatever it was, that's what it was. Okay. But you get v. You got everything you know to get need to get v. You got the radius and the time it takes to go around a circle. So you know everything on the right-hand side. That's just a number on each equation. Just a number here and a number here. No variables, no unknowns. In this situation as we stated it. Okay. M1g cosine theta is known. Okay. That's just a number. So is m1g sine theta if you believe our estimate of theta. Now, our estimate of theta has to be consistent with the length of this thing and the radius. And since we did estimates, our estimates aren't any good. So you have to do a little more work depending on the given information to figure out what these numbers are. If you're given those numbers, the only thing you don't know is f norm and mu f norm. Well, you solve this equation for f norm, you solve this for mu f norm. Now you know what f norm is and you know what mu f norm is, so I'll bet you can find mu. It's that simple. In the simple case. Now, it could be the information's a little bit weirder, and then you have to do more with it. But just analyzing that problem is a pretty good illustration. And you got a problem similar but not the same as this one in the homework. Okay, you're going to have to do a similar analysis, and I'm not going to tell you which problem it is. you should recognize it when you see it. You should recognize the situation. At least the important properties of the situation. You keep looking at this thing. I see everything is pretty reasonable, readable. It's not all that fuzzy, but I swear there's a little fuzziness to it. Okay. So just in case all that was a little fuzzy. There it is in all its glory. Okay. Interestingly, if I move this board a little further over, then it's going to spontaneously tilt. Okay. If I put this up against it, gives us a normal force between this and this, and also a normal force between this board and the one behind it. What's the coefficient of friction? One board and another. We can figure that out just by taking a similar board. We'll assume they have a similar coefficient of friction. Okay, so I can take this board and I can mess it up. I can this board upside down the top of it. And then carefully, I can tilt this board until that one slides, which is right about there. There it goes. Okay. So that angle, tangent to that angle, is your coefficient of sliding of kinetic friction. Okay. No, sorry, coefficient of static friction. Then once it starts sliding, we got to reduce the angle a little bit to keep it sliding at a constant rate, which is going to be difficult because it's a little jerky. It's not a constant, really constant normal force or constant frictional force. But you should recognize what I'm talking about. Okay. It comes down to coefficient of friction is the tangent of the angle at which the thing is just ready to break equilibrium. Okay. Okay. It's a tangent of the maximal angle that keeps it in equilibrium. If you go beyond that angle, start sliding. Okay, well, that is just an aside. Got a block here on this plane, and we're gonna push it with a force at some angle other than parallel to the incline. Now, it isn't necessarily horizontal, but I drew it that way. We'll do the horizontal case, but I could have this angle being some angle phi, say, phi being the Greek letter between phi and pho. No, it's between pho and thumb. Geez, I don't know the alphabet anymore. It's terrible. Okay, I need to get more sleep. Okay, so we got some force here. I'll call this an applied force. Horizontal. Okay. Now we still want to analyze this situation with axes that are parallel and perpendicular to the incline. Pretty much always want to do that. But of course, now this applied force isn't parallel to the x-axis as it would be if the x-axis was horizontal. Okay. But it could be at any angle. So my question is, what's the free body diagram look like? Assuming coefficient of friction is mu. Now, don't specify mu static or mu kinetic. And, problem you might see in open math, in the earth materials. Might. Okay, so draw me a free body diagram. Kind of quickly. Whoops. No, I don't want to